All right, kids, here we go. Thermochem homework number 4. Question 1, draw a bomb calorimeter. A bomb calorimeter is a machine that's going to measure the amount of energy that's in food. The original small part that we're going to put in the middle is called the bomb part. The bomb part is where the food goes. And where the food goes is going to have a little container, I suppose, and we're going to have to be able to pump it up full of oxygen, and it's going to have a couple of wires going to it in a little while. The bomb goes into a tank of water. This is an insulated box with water in it. We're going to use pure water too. That's going to be very important. You want to use distilled water so that the specific heat capacity constant for water is going to be exactly 4.18 joules per gram dot Kelvin. Now, through the top, we're going to run a wire. I use some curls so that you know it's a wire. It's not just something weird. Well, it looks weird. This is an electric source, E-L-E-C-T-R-I-C-I-T-Y. Electricity is going to be able to go in there. We're going to also pump it up full of oxygen before we put it in the box. In the box, there's going to be a very fancy thermometer. A thermometer that's going to tell the exact temperature of the water. We're also going to be very careful, and we're going to get the mass of this water exactly. And what happens is, we know the mass of the water, we know the starting temperature of the water. After we spark the food with electricity, it's going to burn to a crisp with the oxygen, and heat is going to come out. Heat will come out in every direction. In the box, there's probably also going to be a little propeller that's going to spin and mix the water up so that the hottest water around the box will mix with the rest of the water. So we'll be able to, after we burn the food, see what the temperature of the water has become. Now think about this. Q equals mc delta T. The amount of heat is going to equal the mass of the water, which we know what it is, times 4.18 joules per gram dot Kelvin, which we know is a constant. And we're going to measure the delta T. We're going to have a start and end temperature, and the start and end temperature is going to be the delta T. We'll be able to measure how much energy the water gained, and then we're going to say, well, of course, that energy came out of the food. And then we can say that much energy comes out of the food. We'll be able to figure out how many joules of energy comes out of the food. We'll be able to change them into cals, and we'll be able to change them into food calories. And so we'll be able to decide, once we burn the food up, how much energy was released by the burning of that food. Now, burning food is different than eating it, but the same amount of energy comes out when you burn it as well as when you digest it. So if we burn up some potato chips and they give off 100 calories of energy, if we eat that many potato chips, we will biochemically digest that amount of food, and it will give us the same amount of energy. Okay. Now, question number 2, I'm going to move this up, and you won't be able to see the question, but I need some room to write. It says 102 mLs of water is at 278 Kelvin to start. It gets 38780 joules of energy. And what is the final temperature of the water? Now, we've not done a question like this, but this is a formula that we're going to use, that we've used the formula before, but we've not looked for the change in temperature. Q equals mc delta T. The amount of energy is equal to the mass times the specific heat capacity constant times the delta T, or the change in temperature. Now, we don't have a delta T. We have a starting temperature, and the question is really, what is the delta T? what is the final temperature. So the number of joules, 38780 joules, is going to equal 102 grams. Now the mLs and the grams are the same because this is water, and water has a density of 1 gram per 1 ml. So for water, mLs and grams are interchangeable. Water has a 1.48 joules per gram dot Kelvin specific heat capacity constant, and then delta T is going to be our unknown. We're actually trying to find out the final temperature, but really, we can't find that out. We can find out what the change in temperature is, and then we're going to have to do one more step. So to get the delta T by itself, we're going to do 102 grams times 4.18 joules per gram dot Kelvin on both sides. 102 grams, 4.18 joules per gram dot Kelvin. On the right side, the grams and the specific heat capacity constant cancel, and we're going to get delta T equal to, now mathematically, we have a lot of units in here. We have joules in the numerator and joules in the denominator. Here, we have grams in the denominator, and this is grams in the denominator of the denominator, so they get to cancel as well. Strangely, this last unit, Kelvin, is in the denominator of the denominator, so mathematically that's going to pop out into the numerator again. And we have this number, 38780 divided by 102 times 4.18. That's the math. So I'm going to get my calculator, and I'm going to do the 102 times 4.18. And so I'm going to rewrite this as 38780 divided by 426.36 K equals the delta T. So I'm going to divide 38780 divided by 426.36, and I'm going to get 3 significant figures here, I think. Yes, 90.95. That's going to be 91.0 Kelvin is the delta T. Now, some of you are going to think, uh-oh, there's the answer. What's the question? What is the final temperature when that much heat is added to water at that temperature? The final temperature is going to be 278 Kelvin plus 91 more. We're going to add that much temperature to the starting temperature to get the final temperature. So the answer is going to be 369 Kelvin. Be careful, because you have to answer the right problem. When you have multiple equal signs in your process, you have to think, what is this equal to? Does it equal to something, or does it equal to the answer? Am I answering the question right now, or am I answering parts leading up to the answer? And in this case, the 91.0 Kelvin is the delta T. And that's correct, but that's not the question. The question is, what's the final temperature? 369 Kelvin.